We all want useful quantum computers. Fundamentally, I believe that this is the reason why we're all here in this community, and every year coming back to Q2B, which I think is every year becoming a bigger and nicer and more to-the-point conference. And we want to reach this useful quantum computing regime. But as we all also know, there are very challenging obstacles along the way. In order to build a large-scale fault-tolerant quantum computer, there are many challenges along this road that we need to overcome, and they lie across the entire quantum computing stack. So from the QPU through the control hardware layer, the control software layer, and then the applications layer. But while the challenges lie across the entire stack, really, still, in some sense, the main challenges to build a large-scale quantum computer, a useful quantum computer, lie in the QPU. Still, our main challenges is to build better and better qubits with lower and lower error rates, higher coherence times, and that's where there are some fundamental challenges that we need to deal with. But very interestingly, in the last several years, we're seeing more and more an interesting concept, which is our ability to offload some of the challenges to the control layer, both the control hardware and the control software. Today, I'm going to focus on the control hardware layer. Later on, we have Mike and Joe that will talk more on the control software side of things. But we're seeing more and more this opportunity to offload some of the challenges into the classical layers, the classical control layers. And we have very, very mature classical computing technologies. So if we can even compensate, even overcompensate with our classical control systems, hardware and software, for some of the challenges we have in the QPU, then this is an interesting approach, at least until we have the perfect qubits. So this is what I'm going to tell you about today. I'm going to tell you a little bit about our perspective. How do we see this opportunity to offload some of the challenges from the QPU to the control hardware system? And then I'll tell you a little bit about what we at Quantum Machines are doing in order to push this topic forward. Okay, so we're seeing really, we identified 4 key aspects that are important to allow us to allow the control hardware to sort of carry some of the burden. And those 4 elements are scaling up, analog specifications, quantum classical integration, and programming flexibility. I'm going to tell you a little bit about each and every one of those, and then tell you what we do at Quantum Machines to meet some of these challenges. So scaling, it sounds pretty trivial. You have a small quantum system, and so you have a small control system. You have a large quantum system. You have a large control system. But this is not that trivial. In fact, with classical computers, the control system does not scale linearly with the size of the computer. But in quantum, it does. And the reason why it does is because we don't have perfect qubits yet. So instead of doing things sequentially on our large quantum processor, we're still parallelizing all the operations because we want to squeeze as many operations that we can in a given time, in the given coherence time. And that's why we're seeing these big control systems. So that's going to become more and more challenging, but we know how to do it. We know how to scale to thousands of qubits in terms of a control system. You can see those pictures are for control systems that are for tens or hundreds of qubits. Now I want to go to the thousands of qubits. This is a very challenging task. Simply scaling up. And scaling up doesn't just mean the number of control channels. It also means the density of the channels, the synchronization between them, as well as the price per qubit, the price per channel or control channel per qubit. So that's scaling up. And very related to this is the analog specification side of things. We need to really optimize the performance of this control system to push fidelities to the limit. And we need to do it at scale. And the reason why this is offloading the QPU is because we have theories that says that with very simple set of gates, we can do any quantum processing that we want. But we're actually using a much, much richer gate set than the necessary, than the theoretical universal set of gates. And the reason why we do it is because we want to be able, again, to optimize the circuits that we want to run much better. So one example for that is an I-swap gate. You don't need to have an I-swap gate in your quantum computer. You can have only a C0 gate in your quantum computer. But if you have both a C0 gate and an I-swap gate, you can optimize circuits. You can squeeze more gates on the abstract level into the real gate set of the machine. Okay. But the issue with this is that it puts more overhead on the control system. Certain new types of gates require give new requirements on the control system. So for instance, these I-swap gates for superconducting qubits implementation, at least some superconducting qubit implementations, require very good phase coherence between channels, and that is becoming even more challenging as you scale your quantum computer, meaning that you need to have thousands of channels all synchronized in terms of phase. You cannot have drifts in your signals, and that puts a lot of different considerations on the control system. So that's the second kind of type of element that we need to really work on the control system in order for them to be able to provide us with a richer richer set of gates to, again, squeeze more out of the quantum processor. The third element is quantum classical processing. This is a topic that's very, very close to our heart at Quantum Machines because our technology, our core technology is about quantum classical processing. We've heard about this quite a lot from Nicole in the previous talk. So I'll tell you about our perspective on this. So we define quantum classical processing as the following. You need to do some quantum operations on your quantum device, then perform some measurements, send them to your classical processor, classical device, perform some classical processing, classical operations, and then very importantly, generate new quantum operations based on this classical processing. So you really have to close this kind of feedback loop to fall under our definition of quantum classical processing. And interestingly enough, many of the kind of hottest topics in quantum computing today fall under this definition, like active state preparation, repeat until success circuits, adaptive quantum error correction schemes, calibration workflows, variation algorithms. All of these have to do with this quantum classical feedback loop. And we kind of looked at these different use cases and we tried to categorize the requirement from the control layers, from the control system, based on these different use cases. And we found two different dimensions that we can analyze this according to. The first one is what type of feedback, what type of operations, of quantum operations I can generate in response to the classical operation. So for example, whether I just make a decision to apply an operation or not apply an operation based on the classical processing, or whether I really branch the entire quantum program based on the classical processing, or whether I just update parameters of my control sequence based on the classical processing like we do in variation algorithms and certain calibration routines and so on. So that's one kind of dimension, what is the type of feedback that I have in my quantum classical loop. And the second category is what we called the classical feedback latency. That means, the time from the moment I measure my qubits, sending the results to the classical processor, performing my classical processing, and generating new quantum operations, sending them back to the QPU. And we identified three categories of quantum classical processing. The first one, we call it quantum real-time, or QRT. That's where we need the feedback latency to be much, much smaller than the time it takes the qubit to change, the coherence times. So active state preparation, this is an example where you see we measure the qubit, and based on the result, we decide whether or not to apply a certain operation. We have to have the feedback latency much smaller than the time the qubit changes, right? The second category, we call it system real-time, or SRT. That's where we want the feedback latency to be much smaller than the system drift time. One of the major issues with quantum computers today is simply that some parameters of the system drift, classical parameters like the qubit frequency. You see in the red curve there, you can measure a qubit frequency and it drifts, and then all of a sudden it jumps. This is really bad for fidelities. But if we can close this tight quantum classical feedback loop, we can measure the frequencies and correct from our classical control system, we can flatten the curve as you see in this blue or purple curve. So that's system real time. And the last one is what we call near quantum real time, where we don't need the feedback latency to be much lower than anything else, but we want the feedback latency to be much smaller than the total quantum computation time, just in order for it to not bottleneck the total runtime of our application. So unfortunately, this is not the case in many quantum computers today. We spend 99% of the time on the classical side, but as I mentioned, we have great and very mature classical computing technologies. There's no reason why we should not be able to engineer the systems to not bottleneck the entire runtime of the application. So that's near real time. So that's kind of the categories of quantum classical processing, and we need to push each and every one of them in order to, again, squeeze more out of the QPUs. Again, at least until we have perfect qubits, we have to really push on all of these fronts to squeeze more performance out of the QPU. The last category is programming flexibility, and maybe that's a little bit less about squeezing the QPU for performance, but it is very important for us in order to learn how to build better QPUs, because if you want to implement, for instance, something like this active state preparation, and you do it and you have very low-level APIs, you program your active reset protocol. It's on an FPGA, for instance, because you need this real-time performance, and it takes you 3 months. And then you need to tweak something small in your algorithm, and then it takes another 3 months. So that's not good. We don't want to program hardware. We want to program software. We need to do those iterations very quickly from software. A good example for that is also quantum error correction. So you can go and build your decoder on an FPGA, or even think about building an ASIC to do the quantum error correction decoding. But at this stage of the game, where we don't know yet what is the best decoder, we have to build systems that give us the right latency for quantum error correction decoding, but allow us to tweak and change the decoder schemes, the decoder algorithms from software. And I'll tell you a little bit more about it in a second. So this programming flexibility, we're going to see a lot more of that in the near future. And that's kind of in order to, again, help building better QPUs and squeeze the QPU for more and more performance. This is the kind of things that we need to think about when we build quantum control hardware as well as software. So I want to tell you a little bit now what we do at Quantum Machines in order to address all of these challenges. And we can address these challenges. In some sense, it's easier than building perfect qubits, right? It's very hard, but as I said, it's classical electronics, hardware and software engineering. We know how to do it. We just need to do it very well in a very suitable manner for quantum control. That's what we do at Quantum Machines. We are all about building control systems for large-scale quantum computers without compromising on performance, because again, we need to push the performance, in fact. So in 2019, we launched our first product that is called the OPX, and that was a shift of paradigm from what we call a memory-based approach to quantum control to a processor-based approach to quantum control. Back in the days, people used to control quantum systems with a control system in which you would generate all the signals you want to send to the QPU in software and then load them into a big chunk of memory. Then you hit the play button, and then the controller just plays like an iPod, all the songs to the QPU. But our approach, the processor-based approach, says that there needs to be a processor inside, a special processor inside the control system that generates all these signals in real time. And that's what we did in 2019. And that's already like the most intimate quantum classical integration right there, because we've integrated classical compute engines into the heart of the quantum controller. So you can do this general classical processing from the controller in the tightest quantum classical loop that one can imagine. So it's kind of like the difference, this change of paradigm from teaching your kid math by teaching them how to do, how to memorize long multiplication tables and division tables, versus just teaching your kid math, right? So that they can do math, and then they can do really complicated math. And so this is what we did, and these are just some examples from our customers how this can really accelerate and improve performance of quantum processors. I don't have time to go into all of these different examples, but you see that we can sometimes speed up by orders of magnitude state preparations, like this quantum real-time example from Caltech, 10-qubit state preparation, or we can really improve calibration routines by this system real-time approach of correcting for drifts in the system, or we can speed up dramatically, sometimes by a few orders of magnitude, actually, calibrations, characterizations, and applications with the pulse processor, because it's generating on the fly all these signals and not wasting time communicating with other classical instruments. So this is what allowed us to grow quite significantly. We have a very large customer base today, more than 250 customers across the globe, including corporate, startups, national labs, HPC centers, and academic institutions. All are using our control systems to either build or use quantum computers. We are more than 160 people in the company, and our customers keep generating high impact on the field every year. So now we want to kind of go to the next steps, because with the pulse processor and the OPX, we actually kind of solve the classical processing side and also the flexibility, because we developed a programming language that allows you to program these real-time quantum control sequences very intuitively. But we need to go to the right side of the chart on scaling and analog performance. And so yes, this is a very dramatic effect. I wasn't sure if the sound was going to work, but this is our OPX 1000. This is our new control system. It's right here in our booth. You're welcome to come and see it. It's a massively scaled up quantum control system. I believe the highest density of control channels that exist today in the market, at least to our knowledge. So you have, again, the highest density of channels for a single quantum control box, but you can stack them together to basically control thousands of channels in a single rack. So that's very important when you scale up quantum computers today. It's also, we kept this, what we call the OPXness, all this real-time pulse processor approach, and how easy it is to program these quantum classical programs. And we've made significant improvement on the analog performance with state-of-the-art analog specifications. Not going to go into the specs, but we've picked the very, very important specs to optimize certain gate schemes in quantum computing. We also made the system data center ready, which means that it's ready to go into real production environment with hot swappable component, redundancy of single point of failure components, monitoring, etc. And so we're kind of making this leap now from an R&D quantum control system to a data center ready, large-scale quantum control system that supports the largest quantum computers out there. Finally, in the last minute that I have, we're not just scaling up the control system, we're also scaling up this quantum classical integration capabilities that I told you about in our partnership with NVIDIA. So the pulse processor, it has these classical processing engines, the closest possible to the qubits, but the processing power is somewhat limited. So now we're taking the next step and we're integrating with heavy, high-performance compute engines like the NVIDIA Grace Hopper platform. We're creating an ultra-low latency interface between the control system and NVIDIA's GPU to provide the best performance in like QPU, GPU, or QPU, CPU integration. That's the product called DGX Quantum that we're developing these days with NVIDIA. We can tell you more about it. And with that, I think that I can thank you, and I'll be happy to maybe get one or two questions if we have time.